all we were doing, we just entered all of our numbers in here, and we were talking about if I were to put all of these on a dot plot, okay, and the mean would be right here at 7, I could find all the distances, like between 1 and 7, and there'd be 2 of those, right? So 6 would be there twice. To find those, we don't need to draw the number line or the dot plot. It's a simple subtraction. All I'm doing is taking each observation, each x, and subtracting the mean from it. So in the next column, I'm going to take every observation minus and subtract the mean. So 1 minus the mean of 7 is negative 6. 13 minus 7 is 6. 11 minus 7 is 4. 1 minus 7 is negative 6 again. 5 minus 7 is negative 2. 9 minus 7 is 2. 6 minus 7. I'm just taking the observation right here and subtracting the mean from it. It's the difference between, the deviation from the mean. Another word for that is the difference. 5 minus 7 is negative 2. 8 minus 7 is 1. 11 minus 7 is 4. All right, so now I'm going to just talk for a little bit, and we're not actually going to do this calculation because it probably won't work, okay? But I want you to listen. Now, the standard deviation is the average distance from the mean. Aren't these the distances from the mean right here that we just found? Add them all up and divide by 10, right? Wouldn't that be a great idea to find the average distance or deviation from the mean? So real fast, you try to do that. Add those up and divide by 10. Yeah. Zero. Does that really tell us anything?
No.
I mean, are all of these observations on average 0 units away from the mean?
No.
No. So our idea of adding up the differences and dividing by 10 is not going to work. And the reason is because some of those differences are negative and some are positive, and the mean actually balances out those differences. So you would hope that these all add up to 0. Okay? So, and this is, statisticians, mathematicians wanted to find a measure of spread. So this is a made-up formula that they used and still use. Okay? So what they decided was, I don't want, those negatives are causing me problems because they're making it all add up to 0. So what I'm going to do is I'm going to take those differences and I'm just going to square them. Because squaring makes it all what? Positive, right? Squaring a negative number makes it positive. So this thing means I'm just going to take the answer I just got over here and I'm going to square them. So negative 6 squared is 36, and 36, and 16, 36, 4, 4, 1, 4, 1, 16. Okay, now that greatly inflated the differences, didn't it? Yeah? Aren't those numbers a lot? 36 is a lot bigger than 6, right? But when you describe distance from something, aren't you really describing a positive value? Okay? Now don't ask me why they didn't just change them all to absolute value and add them up. Okay? Don't ask me why. Okay? Somebody decided this would be better. So that's what we do. It's very consistent through all statistics. Okay? So these are all of the squared deviations. These are called the squared deviations. The squared differences from the mean. Okay? So now what we do with those is the idea we had over here. We were going to add those up. But we don't divide by 10. Especially when we're dealing with a sample. And we'll learn about a little bit why later on when we learn about degrees of freedom. Okay, degrees of freedom has to do with testing, and it's why we don't just divide by 10. Okay, so at this point we're going to add all of these values up. So we just add them up. 154. So these, the sum of the x minus x bars squared. Okay, that symbol means add up all of these. gives us 154. We then divide that by n minus 1 rather than just n. So 9. And then what we do, what? Then we square root that whole thing. And what does that square root kind of take care of that we did already? We squared, so now we're square rooting to get it back down in the correct range of values. And the letter we use to represent standard deviation is an S with a little X down there on the bottom. That means standard deviation of X. Okay, so this is not the same formula as the one that you see below. This is different. This is the one I'm putting this box around is the one that you are going to use most all the time. Okay, all the time. So the standard deviation of this is, now let's do it without taking the square root first. Okay? 17.1. Now, if you get the standard deviation of 17.1, you should always kind of think about the answer you get. If you just get 17.1 and forget to take the square root and write 17.1 down, that should not make sense. Were any of these differences anywhere near 17? No, the average difference from the mean is basically, it needs to be somewhere, if I were to add all those up and divide by 10, it should be somewhere within that area. So 17.1 can't be right. So take the square root of that, and what do you get? You get the standard deviation is 4.14. Is that more of what the average of these might be? Yes. So the standard deviation is 4.14. This measures how far away, on average,
That'll be like what we have to do on our test.
this will be like what you have to do on the test. For one problem, less data values than that. Okay, you have to do it one time. Yeah, okay. It's easy. Good. All right, now, if we had the entire population, we would use sigma. Now, I told you this was sigma. This is capital sigma. This is little sigma. This little thing here. Sigma represents the population standard deviation. Sigma denotes the population standard deviation, or the true mean, true standard deviation. And in that case, the formula would look like this. It would say sigma with a little x. It would have all of the observations minus the true population mean. And if we had that, then we could just divide by n. Degrees of freedom has to do with errors. Okay? That's what it has to do with. We'll learn about that later. It actually takes calculus to prove every one of these formulas. That's not a prerequisite to this course, so obviously we aren't going to worry about that. How to find it, what formula to use, yes. All right, the square of the sample standard deviation. Okay, the sample standard deviation squared is called the variance. And we'll use the variance later, but not now. You might need to know what the variance is, that it's the square of the sample standard deviation. All right, so in the last set, what if 41 is standard deviation a resistant measure of spread? That's the main question we want to answer. Okay, I don't think we need to recalculate. If you think, you should be able to do it fast. Let's just think about what would happen here. If the last data value were 41 instead of 11, what would that difference be? 41 minus 7 would be what? 41 minus 7, 34. 34 squared would be a really big number, right? So this would be a really big number. So when you add all of these up, would the number be bigger or smaller than this?
Way bigger.
Way bigger. Wouldn't you still divide by 9?
Yeah.
And still take the square root?
Yeah.
So is standard deviation a resistant measure of spread? No. Standard deviation is not a resistant measure. A resistant measure means not affected by outliers. Okay? Studying. Not just, oh, I heard it once in class, I'm going to remember it. That's not the way this class is going to work. you're gonna have to review these things. All right. We are almost done. Okay. Now, we're about to learn something absolutely amazing here before we learn how to do this. You all have textbooks, right? Some of you haven't cracked them open except to look at the homework. How many of you have read all the assigned pages? Okay, that's good. Did you notice things like on page 14 in your book?
Should calculate steps.
Okay, so we just followed the stat, edit, and we entered all these things, and that's everything's in the list now. Okay, now, you want to make a histogram? Okay, get out a piece of paper. No, just kidding. Your calculator will do it, and then you can draw it on there. Did you know that? Did you know that? Did you know that that's also in your book, where to make a histogram? What? Yeah. Okay, so I'm trying to find where it is in the book. Oh, look, there it is, making a histogram. Page 46, make a histogram. It's more detailed instructions there. Did you know that they were there? You should have if you read the book. Okay? Your calculator is one of the most amazing things that you have for this class. All right, so I want to make a histogram. So now I need to hit second. It tells me right here to hit the stat plot button. Well, where's that? It's above the y equals. To get to it, you hit the blue second stat plot. You need to go to plot 1, should be highlighted, hit enter. You want on to be highlighted. If off is highlighted, you have to hit enter so on is highlighted. There are 6 types of graphs. A scatter plot, a line plot, a histogram, 2 kinds of box plots, and this is called a normal probability plot, the last one. So you can move your arrow around and highlight the histogram and hit enter. You need to tell it where your data is. It should be in list 1. And then you can just hit graph. Now, if yours isn't like mine, isn't mine beautiful?
Yeah.
If yours is not, what does it tell you to hit?
Zoom.
Zoom 9. Hit zoom 9. It's statistical zoom, and it'll put it all there. What if you want to know the numbers? Because if you draw a histogram like this on your paper, I'm not giving you any points. Because to me, you just drew some boxes. Are you listening?
Yes.
Okay. How do you get the numbers to show up? It tells you right in your notes. After zoom 9, what does it say?
Trace will show you.
Trace. Hit the trace. I'm not even looking at my book. This is the short version in your notes of this. Trace. Then you can go and see how this first bar of my histogram is highlighted. It tells me that that bar goes from 2.4 up to 5.6. And then if I use the over arrow, it tells me that this bar goes from 5.6 to 8.8. And then so I should be able to recreate this on my paper. It also tells you here, like this, n equals 2 means there's 2 observations in this bar. The next one has 4. So that's telling me my scale on my vertical axis when it tells me how many are in there. Amazing, isn't it? The bad thing about a histogram on here is it really never picks really nice little ranges. Now you can go to the window and you can do the X scale. You can make the histogram be a certain width, like 3 or 5, so it's nice. So if I wanted to just make it all 3s and then graph it again, it's going to change the number of bars that I have, and then when I hit the trace button, okay, they still started at 2.4. Then I'd have to go, see, I could hit my window. If I wanted my X values to start at 2,
2 works.
2 works, and then my maximum to be 22, and I want my scale to be what?
I did 2.
2? See, this time I changed mine a whole lot, and now when I hit my trace, it'll give me really nice bins, 2 to 4, 4 to 6, 6 to 8. So you can tell it what size bins you want, where you want, you know. Isn't that nice? All right, so now what else can you make?